So time to talk about the normal random variable. And we're ready to, we've sort of hinted around about it a little bit before, but now we're really ready to look at its PDF. So let's write down that baby. If a random variable x is normal, it is a PDF that looks like this. And it's kind of something else. 1 over root 2 pi times sigma, that's a parameter, and sigma is not under the radical here, so I'm writing it, times E, Euler's constant, the same E that like showed up in the Poisson distribution as well. And E is raised to a power, let me make that a little bit neater here, the power x minus mu squared over 2 sigma squared. So this whole thing is the exponent that we're raising e to. Okay, that's it's got a lot to it, that PDF. What do I want to say about it? 2 parameters. That's really the important thing. So mu, this parameter, is the mean, it's the expected value of x. Okay, so that's kind of nice. The PDF is big and hairy, but the expected value is just sitting in there. We can just read it right off. And sigma, I'm going to say sigma squared is the variance. I could say sigma is the standard deviation. So those are the moments of the normal random variable are the parameters of the PDF. So there's no tricky business of calculating them. If we want to talk about which particular random variable in the big family of normal random variables we're talking about, the way we do that is we identify the mean and the variance or the standard deviation. Because the normal distribution is what we use so often in statistics and data analysis, it's not uncommon for people to just talk in terms of sigma, in terms of the standard deviation, which is fine. It's always fine to do that. It does mean you kind of have to make sure that you know what people are talking about, okay? So in particular, if you see somebody writing x is distributed normally on with these values, you might want to be careful, or if you're writing this, you might want to make it clear to your reader that this is the variance, implying that the standard deviation is 2, or is it the standard deviation implying that the variance is 16. If I was going to write it myself, or what kind of would naturally spring to my mind if I saw that, I would probably think that it's the variance, but I'm not sure that that's always true. And I was asking myself, well, do people, when people just write x is normally distributed with the parameters like this, do they sometimes mean standard deviation? And I kind of searched around a little bit on the internet, and yes, sometimes they do. So what I would say about that is it is better to avoid this kind of notation and to say something that is clearer. Just write it out in words. Yeah. To be fair, the occasions where people use this kind of notation the most or are frequently involving a standard normal, which we're going to talk about in very shortly, that has variance and a standard deviation of 1. So in that case, it doesn't matter. But if you are actually being told numbers, just make sure that you're keeping your variance and standard deviation separate there. Okay. So two other things to say, two important things to say about normal random variables. Some bad news and good news. Okay, so the bad news is the CDF of the normal. Okay, we can just write it like this. Is the integral of that baby. Root 2 pi sigma e negative x minus mu squared over 2 sigma squared with respect to x. That's what it is, and there's not a lot else to say about it. This integral does not have a nice, what we would call a closed form solution. So I can't do what I did in the last lesson of find the function whose antiderivative, whose derivative is this. I find the antiderivative function for this. There's no nice, clean way of writing down what would go on the other side of the equal sign there. Okay. That's bad news. It's not that bad of news. Even if we can't come up with a nice, neat mathematical expression, we can numerically calculate these values, kind of using the adding up rectangles algorithm that we learned about in Math Camp, or close variations of that. We don't have to do it. Those numbers have been tabulated, and they've been in tables for honestly for centuries now. So we can just look up the probabilities that we need. So we can look up the answers to specific questions involving cumulative normal probabilities. And we will do some of that in the next lesson. Most of the time, you look it up by asking R or Stata or Excel or whatever package you're working with to give you the probability that you need. Okay, so that is, but it is still kind of bad news. Too bad that the normal distribution that plays such an important role in statistics doesn't have a nice, pretty CDF for us to work with. Some good news, though, I'll go to another page here. I'll kind of write out the slogan version of the good news, and then we'll talk about what it means. So the slogan version is that linear transformations preserve normality. Okay, what does that mean? That means that if we start off with x being normal, what that means is if we apply a linear transformation to x. Okay, so it's same linear transformations that we've been talking about throughout the class. Multiply x by a constant a and add a constant b. So if we do that, ax plus b is also going to be normal. That's not true for all random variables. Like you take a Poisson random variable and apply a linear transformation, and you are not necessarily going to get another Poisson random variable. In fact, there's no way you will. But this is a really nice thing that the normal transformation, the linear transformation, when applied to a normal random variable, means that you get another random variable that has the same basic shape. And so that's another important point to touch base with here, that normal random variables have this kind of famous bell curve shape. I'll draw one freehand here. That's kind of what they look like here. Okay, so if this is x, this is the PDF of x. I'm not going to write out the whole thing here. The center of the PDF is the mean. Okay? So the expected value for normal is the same as this point of symmetry. And that's an important thing. Okay? So the probability that a normal random variable is less than or equal to its mean value is 50%. It's also true that I didn't exactly draw it that way, but there's nicer pictures in the notes. It's perfectly symmetric on either side of its mean. So if we want to know what this area is, it's the same as the corresponding area that's just as far on the other side of the mean. So that symmetry is helpful there. It's also true, although less kind of relevant for statistics, that the mean, the median, and the mode are all the same thing. Okay, so the mean is the expected value. The median is the value that has 50% probability on either side of it, and the mode is the value with the highest PDF value. All right. And what the business about linear transformations preserving normality means is that if we apply a linear transformation like this to X, what it does is, I'll do it on the same chart. I think that's actually easier to do it that way. Okay. So if we're going to multiply X by A and add B, let's say that B is a positive number here and that A is greater than 1, you'll get something that looks like this. Okay, so that is the of AX plus B. This difference that it shifts here will just be B. And it got flatter because it would be flatter in the case where A was greater than 1. A is going to increase the variance. So let's kind of actually remind ourselves of how that works. So this claim about linear transformations preserving the shape of the PDF, true for the normal distribution, hugely useful, but not always true for all distributions. We know some other things that are true for all random variables. Okay, so let's remind ourselves of those. For any random variable, normal or not, okay. Well, we know that the expected value of a linear transformation is the linear function applied to the expected value. That's always true, right? And remember, we also found that the variance of a linear transformation is a squared times the variance of X. So let's put kind of all these facts together. This 1, 2, and 3. And what this says is 1, 2, and 3 imply that if X is normal with mean mu and variance sigma squared, then we know the full distribution of the linear transformation. AX plus B is also normal with mean A mu plus B, which I should have written in here, by the way. And a variance of A squared, sigma squared. So just as we would with any random variable, when we apply a linear transformation to the random variable, we can find the expected value of that new random variable by applying the same linear transformation to its expected value. Okay. Can't do it with other transformations, but we can do it with the linear ones. We also know that when we apply that AX plus B transformation to the random variable. The B part doesn't affect the variance. That's the part of it that's just shifting the random variable towards the positives or towards the negatives, but the one that's multiplying it, the one that's changing the units, you can think of it that way, affects the variance and it affects it as a square. All right. So last thing I want to do is just maybe illustrate that one more time. There's nicer illustrations in the notes, but just talking you through what we do. Maybe I'll start with the black version first. So here's the PDF for my original random variable X, and it has mean mu. And I say one of the things I do is add 3 to it. What that is going to do to the PDF for the transformed random variable X plus 3 is just going to move it over so that the new mean will be mu plus 3 here. And the shape here will be the same. If instead we change the variance or the standard deviation. So actually, let me finish up what I want to say about the expected values here. Adding terms to a normal random variable is just going to shift this PDF to the right or to the left by the amount of B. So here's the PDF of X plus, I said it was 3 there. When we change the variance, we either squeeze the bell curve so it becomes thinner, that's what we do if we decrease the variance, or flatten. So drawing that, start off here. This is my initial one. Let's say that this one has a variance 1 here. If all I do is change the variance of that, that wasn't so good. It has to be curvy. It's not a straight line. That's one thing the normal distribution is. It's not an acceptable version of a normal random variable. Okay, so let's try, and here's another bell curve that has maybe a higher variance. And if I wanted to add something with like sigma squared, it's 1/2 and even lower variance. Okay, so the lower the variance, the more squeezed towards the mean the normal distribution is. Another thing that you might be aware of or might have kind of picked up from the pictures is that normal random variables are defined over the whole real line. These bell curves never hit the x-axis. You know, they get super duper close to it because every one of these normal curves has to have a total area of 1 underneath it. Otherwise, it's not a probability distribution. So they do get super duper close to the x-axis. And what does that mean? Substantively, it means that as you get farther and farther away from the expected value, the probabilities get super duper small, but they never actually go to 0. Okay, so this shifting toward the right or to the left and compressing or expanding, but still keeping the shape normal, this are how the linear transformations look when you apply them to the graphs of the PDFs. So in the next lesson, what we'll do is we'll use this property. We'll use the fact that the linear transformation doesn't change the overall shape. It's always still going to be normal. We'll use that to find the cumulative probabilities for for any normal random variable from a table that applies only to a special one.